So, let us start lecture 35. And we will continue our discussion on kinetics of corrosion. In fact, we have already reached to the state where we can find a relation between current density and over voltage, and that relation we have found in the last lecture, which is I A equal to beta A log of I neta A, which is anodic over voltage, rather high over voltage value, positive quantity I A plus constant. This is, we termed it as a Tafel equation. Similarly, for cathodic over voltage, it was beta C log I C plus constant, and they were, you can, this constant value also, and if we try to write it, the complete one, which is N A equal to beta A log I A by I 0, and here it is neta C equal to minus beta C log I C by I 0. So, this we can put it plus, because I can take this negative sign, minus sign, into beta C, and where beta A equal to R T into 2.303 divided by alpha N F, and beta C equal to R T into 2.303 divided by 1 minus alpha N F. And these two equations, these are same as Tafel. This is for anodic, and this is for cathodic Tafel equation, and this beta C, this minus sign is incorporated here. So, that is what beta C is, basically the negative slope between over voltage and I plot, and this is definitely a positive slope between over voltage and I plot, which is the current density plot, rather I would say log I plot. Log I plot. Now, these two equations we have derived from a basic Butler-Volmer equation. We have two forms of Butler-Volmer equation. One we have found out from consideration of atomic jump from one side to another, which is inner Helmholtz plane to the outer Helmholtz plane, and that time we have this particular energy distribution. Initially it was like this, and then we have considered that the anodic current density is higher than the cathodic current density. So, that is what we have, this kind of energy distribution plot, which this one is alpha N F neta, and this part is 1 minus alpha N F neta, and this is M side, this is M n plus side. So, this is I A, and this side is I C with a negative sign, because it is flowing negative opposite to I A. When they were equal, when I C equal to I A, they are experiencing same activation barrier, but when I A is higher than the I C, then the activation barrier for the forward reaction is reducing. This is my activation barrier for the forward reaction, and the backward reaction we are getting higher activation barrier. So, that is why the rate of backward reaction is reducing. So, that time we are getting a equation of this sort, which is I 0 exponential alpha NF neta by RT minus exponential minus 1 minus alpha NF neta by RT. So, this with this consideration we would get to this particular equation what we have proven in the last lecture. Now, there is one more form which is I equal to NF K0 concentration of oxidant exponential minus alpha NF. If we consider the way we have considered here, I can write the similar fashion, which this one should be Cr, then it would be alpha NF neta by RT minus CO exponential minus 1 minus alpha NF neta by RT, where this neta was taken as E minus E0. And remember, in this case, the previous case what we have seen earlier, if we go back to that particular expression, if you see this, that time we have considered a reducive symmetry factor, that alpha was reducive, but in this current case we are considering oxidative reducing factor, that is where this Cr part is coming before than CO. Now, that time if we consider condition IA equal to IC equal to I0, and that time E equal to E0, and that case R A equal to K A C of R, concentration of R, and since it is E equal to E0, that time we have considered it to be K0, and then I can convert into I A equal to NF K0 Cr, and similarly I can convert RC equal to Kc CO, which I can write in this form C0, and in that case we have considered one more consideration, which is Cr equal to CO equal to C if we consider, and then in that situation K A0 equal to K C0. If you go back in the last lecture you can find it. So, this I can consider as K0. So, I can replace this C with a Cr with C as well as C, because I am considering that the concentration of for reductant as well as oxidant both are same. So, then from this equation I can get I 0 equal to I A equal to I C equal to NF K0 C, isn't it? So, then if I take this C out, then I am getting the same expression here, because this part is nothing but I0, isn't it? So, we are getting the same equation considering the both the roots. One was considering the rate equation, and then another one is the jump system, jump theory, that classical rate theory, and where we are considering the jump of atom due to that vibration of the atoms from one plane to the another. Now, coming back to these two equations. These two equations are very, very important when we try to look at the corrosion part. Now, before we try to relate this corrosion theory, corrosion of metal with these Tafel equations, first see how they can be plotted. In fact, when I consider this over voltage, let us say Na equal to beta A log Ia plus constant, it means that this is potential and this is, that means thermodynamic quantity and this part is nothing but current density. This part also involves current density because this constant is nothing but beta A of log I with a minus sign log I 0. This is the exchange current density. So, this is current density, this is a kinetic parameter. So, this equation relates thermodynamic quantity with the kinetic parameter. That means, whenever we have a current flow, that means the net current flow, we are going to get polarization which shifts the potential due to kinetic influence. And during corrosion, you would see that yes, we would try to shift the potential of a particular metal from one potential to the another, and during that process we can either get higher corrosion or we can control corrosion. So, that would be more scientific ways of considering the corrosion control, and that is what we have considered. We will see that there are two routes of protection mechanism of metals and alloys from corrosion. One is cathodic protection, another one is anodic protection. Until unless we know and until unless we understand this Tafel equation or the relation between current density and polarized potential, till then we will not be able to understand those protection mechanism properly. Now, let us look at, so it is basically relating these two kinetics and thermodynamics of electrode processes, electrode reactions or the corrosion, I would say, because we are considering in terms of corrosion, we are not looking at the deposition part. Here we have to look at the anodic current density all the time. So, let us try to see how it can be plotted in a particular diagram. So, let us try to see the plot between neta A and log I A as well as neta C and log I C. Let us say this side is log I and this direction is, this particular axis is neta. Now, when the system reaches equilibrium, for example, this particular system we have considered M, when it reaches equilibrium, that means I equal to I 0 equal to I A equal to I C and E equal to E 0 if it is in standard condition, that time this is equal to 0. So, this is 0 value equal to 0, and let us say this is that point we are considering, where this is I 0. Now, at this I know that over voltage is 0. Now, if I try to plot neta A, beta A log I A plus constant, so that plot would be this, and if we extend this, it will go through this point, because at this point neta A goes to 0 also, because this term is nothing but beta A log I A and I 0 log I 0, and at this point I do not get any net current, rather I would remain at I0, and the slope is beta A. I can also have a plot between neta C and beta IC. So, that plot would be this one, and if we extend this, this would also follow through this particular I0 point, and this slope is beta C, which is of negative slope, and the relation is neta C equal to beta C log IC plus constant, and here the constant is beta C log I0. Of course, here also this is a minus term, and this minus this beta C is a negative slope, has a negative slope. Now, that means when I am doing cathodic polarization, neta is going down. So, this is neta C and this is anodic polarization neta A. Now, let us see that if we send a preferential current, that means this is IC, this is IA, and when I send extra negative current, then I would get I applied equal to I C minus I A, that is the difference. Now, if I go to a very high over voltage, let us say this is my over voltage 1, neta 1, that time the current densities, log of that current densities, let us say that current density part is, this is minus 1 and this is minus 5. So, it corresponds to the current of 10 to the power minus 5 ampere per centimeter square, and this corresponds to the current of 10 to the power minus 1 ampere per centimeter square. So, that occasion my I applied would be 10 to the power minus 1 minus 10 to the power minus 5, which is equal to 0.09999, and then if I try to take a log of this, it would be close to minus 1, rather minus 1.0004, which is close to minus 1. Similarly, log IC equal to log of 10 to the power minus 1 equal to minus 1. So, that means if I try to plot log I applied, this would also lie on the same point of IC, and remember this corresponds to IA and this corresponds to IC, because this particular point, which is corresponding to current of 10 to the power minus 5 ampere per centimeter square, that time this particular point is lying on the anodic line, anodic Tafel plot, and this particular point is lying on the cathodic Tafel plot. So, this particular point should indicate IC and this one should indicate IA, and here I am putting minus 5 and minus 1 because we are taking log axis. So, we could see that log I applied is also falling on the same point of IC. Now, if we go for a different level of over voltage, which is let us say neta 2, that time this value is 10 to the power minus 4 and this is 10 to the power minus 2. That time also I could see that they are coming close approximation. So, I applied would be equal to 0.0999, and then also I could see that log I applied equal to log of IC. So, that means that time also if I try to plot log I applied, which is the excess current, that the current that is flowing through the circuit would be falling on the same point. But if I go much lower over voltage, let us say this is n neta 2, neta 3, that time this value is let us say 10 to the power minus 3, and 10 to the power this is let us say this point is 0.005, then I will not be able to see that log I applied is equal to log I c, because in this case I applied equal to I c minus I a equal to 0.005 minus 0.00 rather 0.001. So, then it becomes 0.004. So, log I applied equal to 2 minus 2.39, whereas log I c equal to log 0.005 equal to minus 2.30. So, then it is not equal, we cannot say that they are equal. So, that time we see that the log I applied this particular point at neta 3 should be lying left to this. Now, as we go, let us delete this part so that we will be able to understand carefully. As we go closer to this particular point, I could see that that point also would shift to the left, because the difference is log of that particular I c minus I a is not falling on the same I c line, rather it is switching to the left side. And now, once this, as we go much lower over voltage, it is falling on this particular point. Now, finally, when the over voltage reaches to 0, so that means it becomes undefined. So, that point would be meeting somewhere, and then if I try to connect those locus of those points, I applied point, I get a plot like this, where this portion is a straight line portion which is falling exactly on the beta c line, on the neta c versus log I c line. Similar situation we can think of on the positive side. There also it will be similar way we can construct this particular experimental plot, where this portion, which is a straight line portion, is falling exactly on the neta a versus log I a plot. And in fact, this green line is basically the polarization plot or the Tafel plot, we call it Tafel plot. So, this Tafel plot actually can be experimentally determined by sending extra current through the system, through this particular system, and then try to, we just measure the potential as a function of log I applied, and then we get this plot. And interestingly, you see, as the over voltage is very high, then we are reaching towards that linearity of that particular Tafel plot for the anodic as well as cathodic sides, and that linearity will be enable us to find out beta A or beta C. So, this beta A, which are called Tafel slope, this Tafel slope is important factor to determine the corrosion rate or the corrosion current density. We will see later on. So, that means this is the experimental diagram, which is the green line, and that green experimental line has been drawn from the concept of polarization, which is related to this relation or this relation. Now, coming back to this particular general equation, neta c is beta log I plus constant. If we see it carefully, Here we are considering that the concentration on IHP or OHP, they are same. They are not changing during the polarization. And when it does not change during, it is not changing, because if I see the actual system, we have a bulk system where this is IHP and this is OHP, and then we have a bulk system where Mn plus ions are also present. Now, if I try to see the concentration, if I plot this is concentration axis. So, in this case Cr as well as Co, they are similar. At the same time, Co is also the bulk concentration. Of Mn plus ions. So, in fact, we do not get any concentration difference from the bulk to the interface of that electrode, and that time this particular situation is arriving. Now, in fact, if I try to see anodic, this particular reaction which is cathodic reaction, now in that case if we have this continuous cathodic reaction, there could be a possibility that metal ion is consumed heavily, so that there could be a depletion of metal ion at the interface, and so the depletion is with regard to the bulk concentration of metal ion in that particular medium of the aqueous solution. So, that time we have a concentration difference. That concentration difference might lead to some polarization again. That polarization is called concentration polarization. We will talk about that part. But if there is enough supply of these ions to the interface, that means OHP, then we would not experience any concentration related polarization. Now, if we have this condition that the rate of diffusion of ions from the bulk solution is greater than the rate of jump of ions over the activation barrier, that time we can say that the slowest step of the overall reaction is this one, and the slowest step actually controls the overall reaction and overall rate of that particular process. So, then because this is guided, this polarization is guided by the rate of the jump of ions over the activation barrier, we call it activation polarization. And this activation polarization, it has got two terms, Na as well as Nc, which is activation polarization for anodic polarization, and this is cathodic polarization. So, that means we are getting this Tafel equation is basically indicating activation polarization or the rate of the jump of ions or atom from one plane to another, and we will consider concentration polarization in our next lecture. Let us stop here. Thank you.